This week, learn how to take derivatives of potentially noisy data and still get a smooth result using the Savitzky-Golay filter. Welcome to another MetPy Monday. Hello, I'm John Lehman, a software engineer for Unidata. This week, I want to sort of wrap up what we've been doing talking about time series analysis by looking at taking derivatives. So if you've ever taken a derivative of some data, you know that any noise in the data is greatly amplified by doing this. So little wiggles in your temperature trace become very large wiggles in the derivative, and sometimes that can be problematic. So sure, we can smooth the data before we take the derivative, and that certainly helps, but there's a more interesting way to do it called the Savitzky-Golay filter. So in this type of signal processing, we take some number of points, has to be an odd number of points, and we fit a polynomial to them, of which we get to specify the order. And then we replace each of those points in the data with the polynomial fit. And then we move over and do it again. There are some math things that we can do sort of behind the scenes here to make it also produce first and second derivatives for us very easily. So we can take noisy data and get a relatively smooth derivative that's still representative of the changes out. Now, that's a lot of words around something that I think is a little bit clearer if we just go ahead and look at it. So I'm going to do exactly what we did last week, reading in some Mesonet data. So we're going to need pandas, NumPy, matplotlib, and I'm going to import scipy.signal as SS. And then don't forget matplotlib inline. It was actually quite a while before I realized that this filter was already baked in to SciPy, because I had actually written an implementation of this when I was a graduate student and used it throughout my PhD, but of course it was already in SciPy, so as soon as I found that out, I started switching everything over to that. Less for me to maintain, and I trust SciPy's test suite. It's also doing it a little bit faster than the way that I had originally coded it. So we're going to go ahead and read in the data. It's the same data that we were working with last week. So this is the 2018 0111 Norman.mts or Mesonet time series. I'm going to separate based on some arbitrary number of consecutive spaces. Use the Python engine. And skip 2 rows. So just to remind ourselves what this looks like, I'm going to say unfiltered is df tr, and we'll make a plot of the unfiltered data. So there is our frontal passage in the middle of the day. So now I'm going to make a Savitzky-Golay filtered version of this. So SS for scipy.signal, Sav-Gol filter is what we want. So as the name implies, this was originated by Savitzky and Golay. It is one of the most cited papers in the Journal of Analytical Chemistry. Chemists use this filter a lot. And I actually really like it because in some data with sharp breakpoints in it, it does a good job of preserving the trend, but filtering out small number of points that have large excursions from what is the mean by using this polynomial fitting technique. So the first thing that we're going to need is our data, unfiltered. And let's look at the docstring. So it takes our data, a window length, and poly order. Those are the mandatory parameters that we must give it. Window length is how many points are going to be considered, and it must be odd. Polyorder is the order of the polynomial that will be fit to those points. It must be at least one less than window length. So if we have 3 points, we can't fit a 6th order polynomial. But if we have 3 points, we can fit a 2nd order. Granted, it would fit perfectly, but we could do so. So in this case, I'm going to have a window length of, let's say 9. And then I'm going to fit that with a polynomial that has to be 8th order or below. If it's 8th order, it's going to perfectly reproduce my data and not really be of much use. So I'm going to go ahead and say, let's fit this with a 3rd order polynomial. So now let's plot that. Okay, so it looks very similar. You see we're preserving these areas of sharp slope, much like we saw with the median filter last week, but filtering out some of these higher frequency bits that maybe we don't want. So I would say that's not a bad set of parameters. Now let's look at what happens if we take a derivative of this data. So I'm going to say unfiltered first order derivative. For this, I'm going to use NumPy's edif1d. So this is just going to take a strict finite difference in one dimension. E is extended, so it'll be the same number of points of our unfiltered data. And then I'm going to have Savitzky-Golay deriv1. So remember ss dot savgol filter our data 9, and I believe we did 9 and 3. Yeah, so we'll just stick with 9 and 3. Then if we look at the documentation, deriv equals 0. So I'm going to set deriv to be 2. All right, 1. We want a first order derivative. So now let's make a plot of that. So unfiltered deriv 1. And so here you can see how really bouncy the unfiltered derivative is, but our Savitzky-Golay filter does a much better job of trying to get the gist of what we want here. So we expect it to be around 0 most of the time with very small changes, and then a large negative change in temperature per time with the frontal passage. You do notice that we did attenuate that peak quite a bit because we are smoothing over the area of highest change with 9 points here. So we could reduce this number of points. We could go down to say 5. Now we're noisier because we're fitting a 3rd order polynomial to 5 points. So we're fitting more of the noise, but I could reduce that to a 1st order polynomial. So fit a line to 5 points. And this actually looks pretty similar to where we were with 9 and 3. So with the Savitzky-Golay filter, there's a lot of room to change these parameters, play around until you get something that smooths out your data, but produces numbers that you're happy with. As one last demo, I'm going to do the 2nd derivative. So this is the rate of change, or temperature acceleration, instead of temperature velocity, if you will. So unfiltered derivative 2. We're going to call edif1d on the first derivative. And then I'm just going to copy and paste this line. So the 2nd derivative is Savitzky-Golay. And we see that we have an issue. So I'm taking a linear fit and trying to take the 2nd derivative. So that's not going to work so well. So I'm going to go ahead and bump this to a 2nd order polynomial. Rerun that so we get a fair comparison. Now let's take a look at the 2nd derivatives. It's a little tricky to read some of those error messages because they don't tell you in a straightforward way what's going on. So you have to think some about how these filters are actually working. So now we can see temperature acceleration. We see a large negative and then a large positive acceleration as the front passes. So the initial increase of the rate of temperature change and then coming back towards zero, along with some smaller fluctuations in here as well. What you can see, the Savitzky-Golay filter has done a much better job at producing something that's slightly more interpretable than just a pure finite difference. So I hope that you found this useful and that you can use some of these more advanced time series techniques that we've talked about in making your data easier to look at, easier to present, and emphasize the things that you're trying to emphasize and help reduce some of the noise, both in a visual and a numerical sense. I hope that you found this useful, and I'll see you on next week's MetPy Monday.